Okay, it's time to once and for all figure out what's going on with the exponential and gamma in full gory detail. Okay, so that's kind of the goal of this video. So let me share this and we'll get going here. All right. So remember, we were talking about the exponential distribution, and one thing that I was making a big deal about was the fact that this really arises naturally as a consequence of looking at a Poisson process and measuring the amount of time it takes until the first observation occurs. So if lambda is the number of observations, the expected number of observations during some period, then if you measure the amount of time before the first observation, that will have the exponential distribution. But let's actually see why that happens to be the case. Okay, so I'm going to go ahead and share this thing, and we'll do a little bit of work in here. All right, here we go. Okay, so first of all, we have a Poisson process. So let's let y, let's let y equal to a Poisson with parameter lambda. Okay, and we know all kinds of stuff about that. Okay, so first of all, y is equal to, so if I have like an interval of time, who knows how long it is. So this is the observation interval. Okay, so this is the observation interval, okay, observation interval. I don't know if it's an hour, a month, a year, a day, whatever it is, okay? And lambda is the expected number of observations. So y itself is equal to the number of observations during this interval, okay? And the expected number of observations is lambda. Okay, that's the kind of the setup for the Poisson distribution. Okay, so here's what I want to do though. So if I take this interval, okay, and I kind of chop it right here, okay, so this is the first observation. The first observation. Then this right here is what I want to call x. Okay, so x is going to be equal to the time until the first observation. Time until the first observation. Okay, so that's what x is going to be. It is a random variable, and we don't know ahead of time how big x is going to be, and x does not have to be an integer. It could be any real number, okay, any positive real number at all. Positive real number, that's the key. Yeah, so I mean, it could in theory be 0 if we, I guess, had an observation immediately at the beginning, but it's just x really is anything equal to or greater than 0. So really this thing belongs to 0 to infinity. Okay, 0 to infinity. Because in theory, I could, during this observation period, again, it's not as if these observation periods just stop. They continue on after this, right? So I mean, I don't just stop observing necessarily after 1 hour. I might, keep going. So, and I may not have any observations at all, in this first observation period. And it may take a long time to get a first observation. That's why we have to allow for the possibility that x could actually be fairly large. Okay, so let's think about x. Okay, let's think about this thing. Okay, so what's the distribution of x. Okay, so what's going on with x? That's going to be kind of like what we're going to be interested in figuring out here. Well, okay. If x is the time until the first observation, what does that mean happens before x itself? Like what does that mean? What does that mean is going on the interval from 0 to x? Okay, so okay, if the if the event x greater than or equal to little x occurs, okay, then what does that mean? Well, it means that y, remember the y was counting the number of observations, then y is equal to 0 on the interval from 0 to x. Okay, so that is, let me just write this down. That is y had no observations. Y had no observations on the interval from 0 to x. Okay, so that's important. Okay, so the event x equal to or greater than x, which means we're still waiting for the first observation. Okay, x equal to or greater than x, which means we are still waiting for the first observation, means that the Poisson random variable is equal to 0 on the interval from 0 to x. Okay, but what's y's distribution on the interval from 0 to x? Okay, well, let's talk about that. But on the interval from 0 to x, y, the distribution of y, or let's see, the expected number of observations is lambda x. Okay, so it's lambda x. Okay, you kind of scale lambda by x. So z, let's introduce a new random variable, z, which is distributed as Poisson of lambda x. Okay, I'm just kind of fixing this little x value right here. Had 0 observations in the interval from 0 to x. Okay, so if I kind of think of this little x as being fixed temporarily, that's what's going on here. So in other words, the probability, okay, the probability that x is equal to or greater than little x is equal to the probability, I've introduced this new random variable z, which is really just a scaled original random variable y for that Poisson distribution. It's equal to the probability that z is equal to 0. Okay, and remember, what's the distribution of z? Okay, so let's think about this. So if z, okay, if z is distributed as Poisson, oops, I think I was not writing it the way that I was normally was in class. Poisson with parameter lambda x, then the probability that z is equal to, the probability that z is equal to k is equal to e to the minus lambda x times lambda x to the k over k factorial. Okay, that's what the distribution of z is going to be. This is that scaled y random, we scaled this thing by x, right, which is our kind of observation interval. And so the probability that x is equal to or greater than little x equals the probability that z, we've kind of tied these things together, the probability that z is equal to 0. And what do I get if I plug in z equal to 0 into this, or if I plug in k equal to 0 into this? Well, I'm going to get lambda x to the 0 over 0 factorial. That goes away, and I just get e to the minus lambda x. Amazing. Okay, so the probability that x, which is the time to the first observation, is equal to or greater than x is e to the minus lambda x. Okay, so what does that mean for the CDF? Right, so the CDF of x is, okay, let's watch this. It's going to be f at little x. This is the probability that x is equal to or less than x, which is equal to 1 minus the probability that x is greater than or equal to x. Now, we don't freak out about being equal to x because capital X itself is a continuous random variable. And so this ends up being 1 minus e to the minus lambda x. Okay, and this is for little x equal to or greater than 0. Okay, and of course, capital X is only non-negative. Okay, is only non-negative, and therefore it's equal to 0. Let me just go like this. This thing is equal to 0 if x is less than 0. Okay, that's remarkable. Okay, so the CDF is given by that. What's interesting is, in this case, we actually obtain the CDF before we obtain the density. Okay, and remember, how would we get the density for this thing? Okay, well, that's easy. We just take the derivative. Okay, and so the density, oops. And so the density of x is little f of x equal to capital F prime of x, okay, which is, let me just kind of write this down, little f of x, okay, remember it was 1 minus e to the minus lambda x is what capital F of x was, okay, and that's going to be, right, so if I take the derivative of lambda as a constant, yes, and the derivative of the power is negative lambda times that negative sign just gives us lambda e to the minus lambda x for x equal to or greater than 0, and it's 0 for x less than 0. Okay, and that, my friends, is exactly what was written. Over here. Yeah. So let's go back over to here. There it is. Okay, little f of x is equal to lambda e to the minus lambda x. And we see flat out that that this thing arose from thinking about a Poisson process. And the lambda for the exponential is exactly the lambda for the corresponding Poisson process. Okay, so that's an amazing thing to think about. Okay, so and there's our capital F of x sitting right there. Okay, and what about this moment generating function? Okay, so look, I won't. Well, okay, so let's think about this. The moment generating function of this thing, okay, is apparently given by this for t less than lambda. Okay, so let's think about that. Okay, let's think about that together. Okay, here we go. Because we know that the moment generating function is going to really give us everything that we need anyways. Okay, so the moment generating function, let's do that. Okay, that'll be helpful. Okay, so the moment generating function, so let's see here. the moment generating function of this random variable x. Okay, well, what is it? All right, so it's going to be, right, it's the expectation of e to the t capital X, yeah? But here, like we know what the density is. The density is 0 before 0, and then it's lambda e to the minus lambda x beyond that, okay? So it's going to be the integral from 0 to infinity, e to the t little x times times e to the minus lambda x. Oops, I also left out lambda, but lambda, just I can slap that on the outside. Yes, that's a constant, dx. And then, if Paul was in here, he would immediately tell us that, hey, look, I have an exponential times an exponential. I can combine those powers, okay? So I'll play the role of Paul here and just say, hey, we can combine these powers, all right? So this is going to be e to the or e to the t minus lambda, okay? This is all in the power here, x dx. Okay, that's interesting. Okay, and okay, so let's go over to the next slide here. This thing's really easy to find an antiderivative of. T minus lambda, okay, t minus lambda. By the way, the only way that this is going to converge, I mean, think about this. This thing would be obnoxiously divergent if t were bigger than lambda. If t were bigger than lambda, or if t were even equal to lambda, this function would be going to infinity with x, and therefore this integral would not converge. So at this moment, what do I need to be true about t and lambda? Well, t needs to be less than lambda. Okay, if t is less than lambda, then that power is negative, or that number is negative, which will then give me a decaying exponential function, and hence this integral will converge. So I need t to be less than lambda. Okay, that's something to bear in mind here. So let's go down here. So this will be equal to, so just m of t equals lambda integral from 0 to infinity e to the t minus lambda x. Oops. What in the world what kind of nonsense is that? Okay, t minus lambda x dx, okay? So the antiderivative of this is going to be lambda over, right? This is a constant right here. T minus lambda e to the t minus lambda x evaluated between 0 and infinity. Okay, evaluated between 0 and infinity. Now, because t is less than lambda, letting x go to infinity is going to give us 0. Of course, the lambda t minus lambda part, that is just a constant. Okay, so e to the t minus lambda x, that's going to go to 0, and then it's going to be minus that thing evaluated at 0. Okay, so this whole thing is going to end up being minus. So if I evaluate the exponential at 0, that's just 1. So it's going to be minus lambda over t minus lambda. And you might say, what? That looks negative. But remember, t is less than lambda, so it's actually positive. And so what we end up with here is lambda over lambda minus t, okay? Which they simplified to, they just divided top and bottom through by lambda. So let me just kind of put that here. And we get m of t equal to, okay, or what did we have? We had lambda over lambda minus t. Okay, which if I divide through top and bottom by lambda, it's 1 over 1 minus t over lambda. And that's for t smaller than lambda, okay? So there's our moment generating function. That's amazing, okay? And then of course, if you take the derivative, okay, so if you take the derivative, so m prime of t is equal to, right, well, you know, I could write this as 1 minus 1 over lambda times t raised to the minus 1. That's probably the most convenient way to write this, okay? 1 over lambda is actually a constant. So what's going to happen? The negative 1 comes down, so it's going to be negative 1 minus 1 over lambda t to the negative 2 times negative 1 over lambda, okay? Fine. Okay, so what is that? That's just 1 over lambda. 1 minus 1 over lambda t to the negative 2, right? Negative 2. Okay. Okay, and so m prime is equal to that. So if I plug in 0, we get the expectation. So the expected value of this thing is going to be m prime of 0, which is 1 over lambda, which is not surprising based on, we kind of talked about that from the Poisson standpoint. If I have 2 observations in 1 hour, how long do I expect to have to wait for 1 observation? Well, 1 over 2 hours, right? So half an hour. So that kind of makes sense to us. Okay, so what was m prime of t? M prime of t was equal to 1 over lambda, 1 minus 1 over lambda times t raised to the minus 2. So the second derivative, what's the second derivative? Well, it'll be minus 2 over lambda, 1 minus 1 over lambda t to the minus 3 times the derivative of what's inside, which is minus 1 over lambda once more, okay? The second derivative at 0, okay, I just plug 0 into that. It kills, the t kills that negative 1 over lambda thing, and I get 2 over lambda squared. 2 over lambda squared. It's very easy to get higher and higher moments of this thing. It's a very, very easy moment generating function to deal with. But the ultimate here is, you know, we want to compute what the variance is. So what's the variance of x? Well, it's m prime prime of 0 minus m prime of 0 squared, okay? Which the second derivative at 0 was 2 over lambda squared, and this was 1 over, right? So m prime of 0 was 1 over lambda, so squaring that is 1 over lambda squared, which is 1 over lambda squared. Okay. Check, which is exactly what we wanted to happen. All right. So there is that. I think I'm going to stop this right now because I do want to talk about a little bit more in here, just by way of, you know, what these things are actually meaning for the most part. But for right now, I think that should be fine. I want to go talk about the gamma, and I want to talk about why it really is. Let me stop sharing this. I want to talk about why the gamma really is like the number of or the how long one has to wait to have multiple observations. And I do want to talk about the gamma function a little bit, but I'll do that in a future video. Stop this for now. Bye.